Okay, Assalamualaikum and have a good day. Welcome back to our class, for operating system. So we are in chapter 3, processes, all right. Okay, in chapter 3, processes, so 3.1, we will elaborate about there are 4 sub-module under this chapter: process concept, scheduling, operation, and processes, inter-process communication, OIPC. Yeah, all right. Okay, and then next, for the objective of this module or chapter, first, to introduce the notion of a process like a program in execution which forms the basis of all computation. Second, to describe the various features of processes, including scheduling, creation and termination, and communication as well. And next, to learn about inter-process communication. So 3.1, concept of the process. So what's the process? Process is a program in execution. Process execution must progress in sequential fashion. Progress is specific entity stored on disk like executable file. Process is active. Programs become process may executable file loaded into memory. Okay, that's the requirement. They need to upload first, to the memory before execute. Execution of a program started through GUI, mouse click, command line entry of its name, etc. So in order to execute, you click and then maybe you type run in the command line. So that's the things. And then one program can be several processes. Consider multiple users executing the same program. So it will happen. And then example, if 2 users are running a word processor, 2 processors will be created. Next, a process structure. A process is a more than a program code, which is sometimes known as a text section. It also includes the current activity, for example, the value of the program counter, and then the content of the register. Here they call processes register. So the register itself is a content. So it also includes the process stack, which contains temporary data such as function parameters, return addresses, and also local variable. It also includes the data section, which contain global variable. It may also include a heap, which is memory that is dynamically allocated during process runtime. So here are the example in figure 3.1, example of the process in memory. Okay, so there is here is a 0 to make is a location, okay, assigned through a IP. Sorry, the address, IP, not IP address, sorry, the address of the memory. 0 to the maximum depends how big your memory. Okay, we will put in staking like this. Okay. So process states. Process state depict the current activity of a process. When process is executed, the process will change from one state to another. Changes states after an event occurs. A state transition diagram can tell what event causes a process to change state. So process state module, you can see here, all right, 2-state and 5-state model. Okay. So process with 2-state model. Yeah, process can be in one of the following state. Two state, either running or not running. So here the example of the diagram. This diagram called state transition diagram. Okay. So either 2-state, either not running or running. So it's like 1 0 1 0, right? So this is the enter display. What we call this? Transition, when they're moving from one state to another state. In order to change, they need to, use this. Okay, pause instruction order from not running to running. Okay, and finally for exit, they need to activate this exit in order to exit or terminate. Okay, so 2-state model. So here are the example of diagram or queue diagram. So they put in the queue and then they will goes that way. Yeah, and this is a view CPU. So central processor unit, and then they will process. After that, will exit or terminate. Yeah. Okay. So for the 5-state model, yeah, for the state which has a 5-state model, yeah. So as a process execute, it changes state. So 5 states: new, running, waiting, ready, and also terminated state. Okay, every state, okay, like new means the process is being created. So it will be in that state. When they move from new to running, so there is instruction to invoke that or execute that, as I told before. So instructions are being executed. So they will move from the new state to the running state. Okay. Okay, they are moving from that state, moving between new to running. There is a one invocation instruction. Okay, in here, right? Here, this one, like interrupt. This instruction admitted. So the circle one here, they call a state transition diagram. Okay, they are moving from one state to another state. Here, from new to the ready state, and from ready to the running. So what are the instruction they use to move from ready state to running state? So this is the diagram for the process state. Okay, all right. A queue diagram. So this is a queue diagram for the 5-state model. Okay, ready queue. There is a queue, IO queue. This one IO is a IO input output request. In queue time slice. Okay, we got the fork. Later we'll explain about the fork. Fork a child. So to create another process. Okay, sub process. So that's they call fork is like fork a child. Okay, fork is another state. And say we create, yeah, fork is the instruction, fork a child, yeah. So create a child, okay, child process. It's like what you call it, from the inherit. It's like three. There is a parent and child, right? Okay, parent will fork. Okay, another process. So they call a fork. A parent, and then there is a child. Okay, child state. Okay, parent state goes to, so they need to execute a fork instruction. Okay, here they use a fork as a verb. Okay, fork a child. Okay, and then child. And also wait for an interrupt. So there is an interrupt instruction as well. okay, to create another state. Okay, so this is they call this a queue diagram. So this one for 5 state. Okay, modeling. Okay, so queue diagram represent of a process schedule. Okay, this one for 5 state model. Okay. So process description, it always controls all the events that occur in the computer system. Therefore, some data structure is needed to keep track of this information. Yeah. So we got virtual memory and computer resources here. So like this one, computer resources refer to the physical, peripherals, all those like CPU, input, output, and memory. Yeah. Virtual is something is unseen, but is virtual. Okay, it's not physical, so that's a virtual. Yeah. Okay. All right. So this virtual, or they call here process, you will assign to each of the resources. Yeah. The one that the called the solid arrow, it means the allocated, okay, to specific resources, and the one that dotted representing a request. So like P2 request to use IO. Yeah. Information table. OS operating system needs to keep track on the status of each processes as well as the resources available in computer system. Done by keeping the information in a table as well. So to keep that, okay, so they are using the concept of information tables. Okay, so the information will be in the table. Okay, try to imagine that. Okay, so that's logically they say that the information will keep in the table. So table that we normally use in the Excel, so that kind of the information. Like this example also, IO table, file table, this is the name of the table. Yeah, memory table, process table, and many more. Yeah, all right. So, okay, information tables, you can see memory, devices, files, and also processes here. So each of the what you call resources, there is a there is a table to keep all the information to each of the resources. Okay, all right. So memory table, IO, process table, similar here. Okay, they say that process 1, process image. Okay, they will keep in the image for each of the process. Okay, the process image, I mean the whole thing. Let's say you want to repeat again, so we have to running that image. Image for process 1, for example, in this case, yeah, image processes 1, and this is the number of the image similar to others as well for the memory, IO, and file. Okay, all right. So here they call process image. This image means that all the the process they recorded everything. Okay, they will keep in that. Okay, the history, the step by step, whatsoever. So let's say if you want to repeat, they will repeat which image. Okay, we run upload, reload or upload, and then run that image file. Okay, that's the word they use here. Okay. PCB or process control block. Information associated with each process, also called task control block. Okay, CPU state. Okay, we got running, wait, and many more. And program counter is a location of instruction to execute. Program counter. Okay, CPU register is content of all process-centric register. CPU schedule information like priorities, scheduling queue pointers. And so we have memory management information. Okay, it will represent the memory allocated to the process, counting information like CPU use, clock times, elapsing start, time limit, all related the time here, yeah. And I/O status information, I/O device allocated to process, list of open file and many. Okay, so they will keep all the information in the PCB or process control block. A thread. So far, process has a single thread execution by default. Okay, all process in single thread. Consider having multiple program counters per process. Multiple location can execute at once. Multiple thread of controls is a threads. Okay, need storage for thread detail. Multiple program counters in PCB. Okay, they will store everything in the PCB. Okay, cover in the next chapter. What is that exactly mean by threads? It's like multitask. Okay, when you listen my lecture, at the same time you eating, you're chatting, you do other works. That's the concept of thread multitask. Yeah. Okay. Process scheduling, maximizing CPU use. Okay. Quickly switch processor into CPU time for sharing. Sorry, CPU for time sharing, and then process scheduler selects among available processors for next execution on CPU, and maintain scheduling queues of processes like job queue, ready queue, and also device queue. Yeah, and then processes migrate among the various queue. A common representation of process scheduling is a queue diagram. So this one is say that figure 3.6 in slide number 11. Yeah. Okay. So ready queue and various I/O devices. So this is how the structure looks like. Okay, when we have in the little bit what you call little bit big scale, yeah, little big scale. We have a couple of PCB and then some information. So this is how looks like, yeah, ready queue and also various I/O devices queue. All right. So that's the concept they use or architecture they use in order to implement all the, there's a, the concept, the structure, everything in your, what you call this, regarding a process. So in your computer itself. So this is how the structure. Okay, from this kind of the theory, this is how they develop. Yeah, all right. Scheduler. So in OS also there is a scheduler. Very important. We need to have scheduler. Very so here they call here there is a short-term scheduler, or we call that CPU scheduler. So for the short-term scheduler, it will select which process should be executed next and allocates a CPU. Allocate CPU means choose which process and then allocate CPU to that process. Okay, that's the thing. Sometimes the only scheduler in a system, and also short time scheduler is invoked frequently. So they will invoke. Invoke means like a fork. It's like a call. Okay, frequently. So frequently, how long? Millisecond. Okay, must be fast. Okay, because everything is faster now, right? So in millisecond. Okay. So long-term scheduler, yeah. So here they call job scheduler. So job scheduler actually select which process should be brought into the ready queue. That's the thing. Once the previously short-term scheduler, they will assign resources to the process. Now, which process should be brought into the ready queue? Okay, for the long term. Long term is infrequent compared to the short-term scheduler. So maybe it's stated here second, maybe in minutes. Okay, and compare as a compare what you call comparing to the short-term scheduler. So it of course it will be slow because in second and minutes, right? Okay, the long-term scheduler control the degree of multi-programming. Processes can be described as either input output bound process or CPU bound process. I/O bound process spend more time doing I/O, while for the CPU bound process spend more time doing computation, and then few very long CPU bursts. All right. Long-term schedulers strive for a good process mix. So altogether, yeah, schedule. So middle level scheduler, which is for the third layer, found in highly interactive environment. So handle overload or overloadings like remove active job from memory, reduce degree of multi-program, and finally result in faster job completions. So this for middle level schedule. For the single user environment, no distinction between job and the process scheduling. One job active at a time. Receive dedicated system resources for job duration. The one for single user environment. So multitask in mobile system. Some mobile system like the early version of iOS allow only one process to run. Okay, the rest will suspended. Okay, so means got many processes, but only one process will be chosen, yeah, to run at one time. The rest must be suspended. Okay, they put in the suspended mode, for example. So starting iOS 4, it provides a single foreground process, and we have multi background processes. Okay, for the foreground process, control via user interface, and for the multiple process or for the multiple background process, in memory running, but not on the display and with limit. Yeah. Limit includes single short task receiving notification of event specific long running tasks like audio playback. Okay, Android Android run foreground and background with fewer limits. Background process uses a service to perform tasks. Service can keep running even if background process is suspended. Service has no user interface and small memory use. All right. Context switch. When CPU switches to another process, the process must save the state of the old process and load the saved state for new process through or via a context switch. Okay, that's the logic. Okay, because later CPU will continue. That's why they keep the what you call the current, right? The current to be they put in the old because they need to run. Yeah. Context switch. Yeah. Context of process represented in the PCB. Context switch time is pure overhead. The system does no useful work while switching. The more complex the OS and the PCB, the longer they take for the context switch. Okay, all right. Time dependent on hardware support. Some hardware provide multiple sets of register per CPU. This one for multiple contact loaded at once. So context switch is a kind of the process here. It's stated here. Help you understand the means of the context switch. They're trying to moving one process to another process. if there is some requirement, request, or interrupt. So in order to change to another process, like one state to another state, okay, so they need to have the context switch concept there. So they will keep the old process. Here, if you back the transaction, the system must save the state of the old process. Save. The old process must be saved first and load the saved state of the new process through a context switch. Okay, all right. So this is the yeah. Okay, so try to imagine that we got two processes right now: PO1, PO, and P1. Yeah, PO and P1. Okay, P0 or P1. Sorry. Yeah. Okay, got two processes right now. So CPU switch from process to process. So this is how it looks like. So at the beginning, we can see that, okay. Okay, so if there is it takes time also. If you check here properly, so for the P0, so in here, this is a time frame. This is a time, represent a time from here. From here to here is a time. Yeah, time. Okay, so interrupt. Okay, if you look here, they will do interrupt here, and then, or as I told you just now, someone invoke. I don't know whether automatic or not. So for to switch from the current process to the new process, they need to do these kind of things. Yeah. Okay. They will save and then reload a state from PCB1. So actually from PCB, they will goes to here. Okay, whatever. So the new state will reload and then save and reload. Yeah, for the previous one. See, so this is the things that you need to understand. Okay, okay, right. Okay, when to switch a process. So there are many kind of things. Okay, to start it or to invoke. Okay, like just now at the beginning, I mentioned about fork. Fork is one of the things. Fork, the word they use to fork, to create another. Okay, like here, one of the things that went to switch based on because there is a clock interrupt. Process has executed with the maximum allowable time. So there's clock interrupt, so they will have to change. I/O interrupt. So this one may be programmably. Okay, they put a program maybe there's a certain period there is an interrupt for I/O, input I/O. Okay, memory fault. Okay, some error, they need to also to do some switch to work something. I'm not sure yet, but this, for example, memory fault for the memory address is in virtual, so it must be brought into memory. So memory fault. Okay, they want to bring a memory address for in virtual memory, so it must be brought into a main memory. Okay, virtual, so there is a memory fault. So when actually like a trap also, for example, error also there is a switching process will happen also. Okay, when there is an error occur. Okay, runtime error, for example, yeah, and supervisor call such as file open. Okay, that's why when you click open somewhere in your system, in your OS, Windows, whatever, so that's the switching. Okay, when to switch a process. So that action, like supervisor calls, like such a open file open. When you open, click open file means we do interrupt or we do some request. So this is the thing, when to switch to another process. Okay, so here are the list of the activity. Yeah. Okay, operation on processes. So system must provide mechanism for process creation, termination, and so on, as detail will explain later. Yeah. So process creation. A process may create another other processes. Okay, parent process create a child, of course. As I told you, parent and child, yeah, which in turn create other processes, forming a tree of processes. They will create such a tree like below example here. You can see here this, yeah, this thing. And then generally a process is identified and managed through a process identifier or PID. So in order to execute that, there is some theory, some algorithm. Okay, this let's calling that the process is identified through and managed through a process identifier. So a tree of processes in Unix. This is in Unix environment how they represent, yeah, each of the process. Yeah. So process resource sharing among parent and children option. Parent and children may share all resources. Children share subset of the parent resources. Parent and child may be, yeah, they can do for share no resources, unshare everything also is a possible. Yeah. Execution option like parent and children may execute concurrently. Parent wait until children terminates. So this is kind of the, option for the execution. Address space, okay. A child is duplicate of the parent address space. Child loads a program into the address space. Okay, and then in the unit example, as I told, fork system call creates a new process. So this is the one. And then exec means for, because different OS, okay, they are using different name. So here Unix, like in Linux, Unix, okay, we are using this execution. The exec, see what means system call use after fork, replace the process memory space with a new program. So exec, yeah. So this figure shows process creation using the fork system. A program to create a separate process in Unix. Okay, I believe some of you have done this later, or maybe in the introduction, if I'm not mistaken, we have this kind of code to understand. Okay, how it's work. So this is in C, program to create a separate process in Unix. So C program forking separate process. The C program just now illustrate how to create a new process Unix. Okay, after fork, there are two different processors running copy of the same program. The only difference is that the value of PID for the children process 0, while that for the parent is an integer value greater than 0. Okay, maybe this one we can have some lab activity, okay, to do for each of you. Okay, maybe I think in chapter 1 or chapter 2. Yeah, if not in chapter 3, maybe at the beginning. All right. Okay, so that one maybe later we go for that. Yeah. All right. Okay, this is creating a separate process using Windows API. Okay, so this is example of the code. Yeah, extension for creating a separate process. This one they use in Windows. Yeah. Okay. So process termination. A process terminates when it finishes executing its final statement. Okay, and it asks the operating system to delete it by using the exit method or exit what? This one I call instruction. Okay, system call. They put in the category of they call system call. So exit the name of the system call. Okay, in order to terminate. Okay, because once you open, you need to have terminate. Mean return back the memory resources that given to you. Yeah. So at that point, the process may return a status value, typically an integer to its parent process, because we have a child and child, parent and child, so they will return to the parent all the value. So this all is accounted, recorded. So easy for them later on to use, is it empty or not, something like that. Yeah. Okay. So all the resources of the process are deallocated by the operating system. So they will, that's why we need operating system to manage all this. Okay. So this is part, the process termination is part of the logical process in computer architecture. Yeah. A parent may terminate the execution of children processes using the ABORT, abort, okay, abort system call, or about this function name. This one category of system call, yeah, category of system call. So we execute this abort, yeah, function or what called system call, we instruction, so whatsoever. So this will terminate the execution of children processes. Yeah. Some reason for doing this is children has exceeded the allocated resource. There is a timer, maybe. Okay. And task assigned to children is no longer required, of course. So that one also some possibility it will happen also. The parent is exiting and the operating system does not allow a child to continue if its parent terminates. So this is some reason behind that. Yeah. Okay, some operating system do not allow a child process. Yeah. Don't allow a child process to exist if its parent has terminated. If a process terminates, then all its children must also be terminated. Cascading termination means all children, grandchildren, etc., are terminated. The termination is initiated by the operating system. The parent process, yeah, may wait for termination of child process by using the wait system call. Yeah, wait system call. The call returns status information and the PID of the terminated process. Okay, like this instruction. Okay, if you see that, okay, this is the explaining. Okay, like this instruction. You see in the code like this, so this is the explanation what actually it does. Okay, if no parent waiting, so mean did not invoke wait process is zombie. Okay. And then if parent terminated without invoking wait process is open. So this is general term that they are used. Okay. Represent the scenario. So multi-process architecture in Chrome browser. Many web browsers run as a single process. Okay, some still do. In one website causes trouble. Entire browser can hang or crash. Okay, Google Chrome browser is a multi-process with 3 different type of processes. First, browser. Second is renderer. Third is a plugin. Browser is a process managed, yeah, user interface, disk, and network I/O. For renderer, process renders web pages, deal with HTML, JavaScript. A new renderer created for each website open and run a sandbox restricting this and network I/O, minimizing effect of security exploit. And finally, plugin, yeah, process for each type of plugin. So inter-process communication. So processes within a system may be independent or cooperating. Cooperating processes can affect or be affected by other processes, including sharing data. Independent processes cannot affect other processes. Reason for having cooperating processes, okay, like reason having a cooperating maybe we have some information sharing. And also it said that computation speed up for multiple processor running in parallel. So this one can happen also. Modularity is one of the reason. Why do we need cooperating processors? Because we have a modular. Okay, we divide the task to the module by module. So when they are communicating, they will communicate among the modules. So they call this modularity. Okay, so this will call the reason why do we need cooperating, and convenience. So convenient to use. So we need this cooperating also because convenient we can use this and that, plug in, use in any other situation. So this is one of the, all right, the reason for having the operating processors. So inter-process communication. Cooperating processor need inter-process communication, or we call that IPC, to model shared memory and also message passing. Two model of IPC like message passing. Okay, this is the memory. If you can process A, process B, and then for the process A, put here, process B is here. Okay, they put in the queue, right? And process for the shared memory, so process A, and then they will share the memory, and process B also will share together, yeah, the same memory area like this. And finally, the lowest in this diagram is the kernel. Yeah. Okay, we will have some kernel, I think, at the beginning. Yeah, beginning for the kernel. Yeah, kernel. Kernel is a very important part. It's the heart of the operating system. Yeah. So share memory, producer consumer problem. Paradigm with cooperating processes, producer consumer produce information that is consumed by a consumer process. So we have outbounded buffer, places no practical limit on the size of the buffer. We got bounded buffer, assume that there is fixed buffer size. So the detail about the producer on consumer, okay, will be detailed out in chapter 6 regarding synchronization. All right. Producer in consumer problem. Because when we just from the previous slide, okay, regarding the inter-process communication. So all this will, will affect the when we are sharing the value. So here we're trying to solve about the sharing issues. We are using producer consumer problem. So at the one time, only one will produce and one will consume. We cannot allow producer, then we got consumer also. One they produce, the consumer will start consume. So consumer will wait until producer produce a result. Okay, so this is issue. Later we'll explain. But and when we talk about trade also, there is a problem of producer consumer. So if you type in the Google also, you find what is actually the producer consumer problem. So this is happen in when we have a modality just now, right? So they are sharing. Okay, the concept of sharing. So we need to handle the integrity, the genuine, the real data, the consistency of the data. So we need to know the concept of producer consumer problem. Okay, this one for the shared memory solution. Okay, this is the how they declare the shared data. You can see define buffer size, and then they put in the memory, and then this they put the buffer size. They will use a 10. Okay, for the buffer solution is correct, but can only use buffer size minus one element. Okay. Okay, but only solution is correct, but can only use buffer size minus one. Okay, so that one will be Later we'll explain this. While next produce, while true produce, and in the next and produce an item in the next produce, while buffer size equal out, do nothing, buffer in next produce, in in plus one. So this is a buffer size. Okay, bounded buffer, this one for producer. And then for the consumer, if next, okay, item next, consume while true, while in. Okay, kita out, do nothing. And then next, consume. Okay, buffer out. And then out plus one, there's a buffer size. And consume the item in the next. Okay, that's for consumer. All right, so now go for the, so we'll do this activity later. Yeah, all right, don't worry. So today is we just have some lecture, the theory, and then when we do the activity, so our understanding about the concept, okay, will be clear. Okay, all right. IPC, message passing mechanism for processes to communicate and to synchronize their action. Yeah, so they are using message passing. Message system, processes communicate with each other without resorting to share variable. IPC facility provide two operations, send and also receive. So if P and Q wish to communicate, they need to establish a communication link, okay, and then exchange. So implement of communication link, either physical or logical. All right, physical, we are using a cable, or non-physical, logical, maybe we can use, here is it, yeah, we can use wireless for the logical. Yeah, okay. So direct communication, processes must name each other explicitly. Send, for the P, send a message to. So receive Q message mean receive a message from Q. Property of communication link. Links are established automatically. A link is associated with exactly one pair of communicating processes. Between each pair, there exists exact one link. The link may be unidirectional, but usually bidirectional. Yeah. All right. In direct communication, messages are directed and received from mailbox, also referred to as a port. Each mailbox has a unique ID, of course. Yeah. Processes can be communicate only if they share a mailbox. Properties of communication link. Link established only if processes share a common mailbox. A link may be associated with many processes. Each pair of processes may share several communication links. Okay, link may be unidirectional or bidirectional. Operation: create a new mailbox, send and receive a message through mailbox, and destroy a mailbox. Primitive are defined as a send and also receive. Send means sends a message, means send a message to a mailbox A, and also a message for the receive means receive a message from mailbox. Mailbox sharing. So P1, P2, and P3. And then P1 sends, P2 and P3 receive. Who gets the message? Solution: allow a link to be associated with at most two processes. Allow only one process at a time to execute a receive operation. Allow the system to select arbitrarily the receiver. Sender is notified who the receiver was. Synchronization. Message passing may be either blocking or non-blocking. Blocking is considered synchronous, where blocking send has the sender block until the message is received. Then for the blocking receive, has the receiver block until the message is available. Non-blocking is considered as synchronous. Non-blocking non-blocking sends has the sender send the message and continue. Non-blocking receive has the receiver receive a valid message or not. All right. Okay, that's all for chapter 3.